Type a sentence and a picture appears. You have seen that and you mostly believe it now, so make the obvious next wish. Not a picture of a chair, the actual chair. A thing you can spin around, look at from behind, drop into a game and print. The picture took a couple of seconds. For years this took an afternoon, and what came back was often a melted, lumpy mess. Here is the strange part. We had already cracked images. The same machinery should have just worked in 3 dimensions. It did not. Making something you can walk around turns out to be a genuinely harder problem than making something you can only look at, and the reasons why are the whole story. So today, where does a chair come from when nobody modeled it by hand? Start with a problem you would never guess because it sounds like it should not be a problem at all. To make a picture, everyone already agrees what a picture is. It is a grid of pixels. To make sound, everyone agrees what sound is. It is a wave of numbers. One obvious way to write the thing down, and the model just fills in that grid. Now ask the same question for a 3D object and the agreement falls apart. There is no single way to write down a shape. You could store it as a mesh, a skin of flat triangles, the thing game engines actually want. Or as a point cloud, a swarm of dots floating in space with no surface at all. Or as a block of tiny cubes like 3D pixels, simple but heavy. Or as a math function that, for any point in space, tells you how far you are from the surface. 2 of these deserve names because you will hear them everywhere. One is a NRF, short for neural radiance field, where the entire scene is a tiny neural network. Hand it a point in space and a direction to look from, and it tells you the color and density there, and you build the image by adding up that color along each ray, point by point. The shape is not stored anywhere. It lives in the network's weights, and you only see it by rendering. The other is the newest favorite, a cloud of millions of soft, fuzzy blobs called Gaussian splats, gorgeous and fast, painful to edit, and the thing under a lot of the photoreal scene capture you have seen lately. But here is the part you must not miss, because it is the single most common confusion in all of 3D. A NRF and a splat cloud are not generators. They do not invent anything. They are how you reconstruct one real scene that you already photographed from many angles, fitting the blobs or the network until the renders match your photos. That is a different job from inventing a chair that never existed, which is the job we are actually here for. Reconstruct from photos versus generate from nothing are 2 different problems, and people mix them up constantly. Every one of these formats is a real working answer, and everyone trades something away. Fast to render but ugly to edit, or beautiful but heavy, or easy to learn but hard to hand to a game engine. So before the AI can even begin to invent a shape, it faces a question images never have to ask. Make the shape fine, but make it as what? And it gets worse because of a second problem hiding behind the first. The image model learned from billions of pictures. The whole internet is pictures, but the internet is not full of 3D models. Good, clean, finished 3D objects are rare, expensive, and mostly locked inside studios. Where images come by the billion, usable 3D shapes come by the few million at best, which sounds like a lot until you remember it is hundreds of times less. There is no ocean to learn from. So the early researchers were trapped between 2 walls. On one side, mountains of flat pictures they could learn from, but pictures are flat. On the other, the 3D shapes they actually wanted, but almost no examples to study. The move that cracked this open was to refuse to choose. What if you could borrow everything the image model already knew about how the world looks, all of it soaked up from those billions of flat pictures, and somehow spend that knowledge to build something with real depth? Here is the idea, and it is genuinely beautiful. You already have an image model that, shown any picture, can tell you how to nudge it to look more real, more like the words you asked for. That is the entire skill from the painting episode, and we are just going to assume it. Now use that model not to make a picture, but as a judge. Start with a blob. Not a chair yet, just a vague lump of digital clay floating in space, meaningless. Then do this over and over. Point a camera at the blob from some random angle and take a flat snapshot. Hand that snapshot to the image model and ask the only question it knows how to answer. If this were a real photo of a wooden chair, what is wrong with it and which way should it change? The model hands back a correction, this part more chair-like, that part less. You push the actual 3D blob in that direction. Then you spin to a new angle and do it again. From the front, more chair. From the side, more chair. From behind, more chair. Thousands of times from every direction. The blob has no escape. The only shape that can satisfy a flat critic standing at every angle at once is a shape that genuinely looks like a chair from all of them. A real, three-dimensional chair, sculpted entirely by a judge that has never once seen in 3D. This trick has a name: score distillation. And that word, score, is not new. It is the very same score from the painting episodes, one of the three names for the denoising arrow, the direction toward a more plausible image. You are distilling that arrow, the knowledge of a flat image model, down into a solid object. It worked. The first 3D objects conjured straight out of a text prompt felt like magic. But the trick had a flaw baked right into its cleverness, and the flaw is so memorable it became the mascot of an entire era. Remember what the critic is: a flat image model. It knows what a good photo looks like. What it does not know, what nobody ever told it, is which way is front. So picture the model building an animal. It orbits to the front and the critic says, "Lovely, a beautiful face." Then it orbits around to the back, and the critic, with no idea it is now staring at the back of a head, says the same thing it always says: "This should look like the front. It should have a face." So the model obediently grows a second face on the back of the skull. The result was a parade of gentle monsters, animals with a face on both sides, characters with the same front pasted everywhere. People named it the Janus problem, after the old two-faced god who looks forward and back at once. And it was not a random bug. It was the deep flaw of the whole approach made visible. If your only teacher is flat, it cannot teach you which way is forward. Now, before anyone tries this at home and tells me their AI still makes two-faced cats, let me be clear. This is history, not the present. The fix turned out to be almost obvious once you saw the cause. If the problem is a critic that has no sense of viewpoint, then give it one. Researchers retrained the image critic to look at several views at once, with an awareness of which camera angle it was, so it finally knew front from back. The extra faces mostly vanished. I say mostly, not entirely, because that is honest. The classic Janus monster is largely designed out now, but on strange prompts and hidden backsides you can still catch a flicker of it. The bigger thing, though, is what this fix did not solve. Score distillation was still slow. It sculpts one object at a time from scratch, nudge by nudge, thousands of tiny corrections each. A single clean model could take many minutes of patient optimization, sometimes far longer. You are not so much generating a chair as growing one. Fine for a research demo. Hopeless if you need 1,000 props for a game by Friday. So the real question shifted. Not, can we make a 3D object at all? We clearly could. But can we make it fast, the way images are fast? Can we stop sculpting every object from nothing and simply know the answer? And that is exactly the leap that defines 3D generation right now. Stop treating every object as its own little sculpture project. Instead, do the thing that made images explode in the first place. Train one big model on every 3D shape you can scrape together, and have it learn the structure of three-dimensionality itself, the way an image model learned the structure of pictures. Then, when you want a new object, you optimize nothing. You show the model a photo or type a prompt, and it produces the finished 3D shape in a single pass. No orbiting critic, no thousands of nudges, one shot. People call this feed-forward generation because the work flows forward through the model once, and out comes the object. Early versions turned a single photo into a rough 3D shape in a few seconds, down from many minutes, and the exact number keeps dropping with every release, so hold it loosely. But how does a model breathe out a whole object at once? with the same playbook that made image generation efficient. Remember from the painting episode, the model did not paint millions of raw pixels directly. It worked in a small compressed summary, a space of meaning, then unpacked it at the end. The leading 3D models do the very same thing. They generate a compact code for the shape first, a small structured sketch of where the surface is and what it is made of. And one influential trick is where you put that code. Instead of spending it on a full solid block, you light up only the cells that actually touch the surface, ignoring all the empty space inside and around the object, which is most of it. That is the kind of move that makes it cheap enough to do in one breath. And here is the payoff that ties back to where we started. Remember, there was no single way to write down a 3D thing. That compact code can be unpacked into any of them. Want fuzzy splats to look at? Decode it that way. Want a solid mesh for your game engine? Decode the very same code that way instead. One internal understanding of the shape, many possible outputs. The format problem from the opening does not vanish. It just moves to the very last step, after the hard thinking is already done. And under the hood, the engine driving all this is not some exotic new thing. It is the same generative process from the painting episode, lifted into 3 dimensions, plus a small learned compressor that squeezes a shape into that compact code and unpacks it again. Same family, new dimension. So where does it actually stand? The models doing this now are real, and some of the strongest are released openly for anyone to run. From a single photo in seconds, they hand back a detailed, textured object, including the surface materials, how shiny the metal is, how rough the wood. Several even split the job the way a human studio would. One stage to get the shape right, a separate stage to paint on realistic materials. Hand one a photo of a chair and you get back a turnable, textured chair, not a lump. That parade of melted blobs from the start of this episode is genuinely the past. But let me give you the honest edge, because there is one. Getting a shape that looks right is mostly solved. Getting a shape that is clean underneath is the last hard mile. A game artist does not just want a chair that looks like a chair. They want one whose surface is tidy and well organized underneath, easy to bend, animate, and edit. Generated objects are often a little messy under the hood. Technically correct, artistically awkward, like a sentence that is grammatical but no human would ever write. So the frontier right now is not making 3D we can. It is making 3D that a professional can pick up and use with no cleanup, and that gap is closing fast, but it is not closed. So step back and look at the shape of the whole thing. We wanted something we could turn around, and we hit 2 walls a picture never faces. No single way to even write a shape down, and almost no 3D examples to learn from. The first answer was a gorgeous hack. Borrow a flat image model and let it sculpt a blob from every angle, which worked, gave us its 2-faced monsters, and was slow. The leap was to stop sculpting and start knowing. Train one model on the structure of 3D itself, generate a compact code, and decode a finished object in a single pass, in whatever format you need. And one boundary, so you know exactly what you just learned. Everything today was about making one object. A chair, a creature, a prop you can export and hold. Generating an entire world you can walk through, where the ground stays put behind you and the room remembers itself. That is a different and harder problem, with its own kind of model, and it is the subject of its own episode. And notice the thread back to the start of this one. Those navigable scenes are often stored as exactly the Gaussian splats we named earlier, the same fuzzy blob representation, now holding a whole environment instead of a single chair. One last thing said out loud. As objects and images and voices get this good and this fast, the line between filmed and generated gets thin, which is why new rules are arriving that say synthetic content has to be marked as synthetic. We hold the full story of how that works, the watermarks and the disclosure law, for the consequences episode at the end of the season. So the next time a finished, textured object spins up out of a single photo in a few seconds, you will know what just happened. Not magic. A model that learned the shape of the world, handing you a piece of it.